So the next session is FR2. Special session. Over to our friend Paulo.
Thank you, Irfan. Okay, so welcome to the FR2 millimeter wave session. We decided to organize a session on millimeter waves because, you know, there is a lot of opportunities on spectrum or millimeter waves, but it comes with a price of path loss. You usually need line of sight, so a lot of challenges. So the idea is how OpenAirInterface can help to understand these challenges and to overcome these challenges. So we need actually research platforms that are able to make us aware of the challenges and find solutions. So our first speaker is Professor Raymond Knopp. He is president of the OAI Software Alliance. So I would like to welcome Raymond to give a talk on the millimeter wave research activities at EURECOM. So please, Raymond.
Thank you, Paulo. There's a lot of people working on FR2 or at millimeter wave at EURECOM, so I'm trying to collect a little bit of what's going on, also what's going on in the OAI software, because there's some very recent stuff that I can say here. So maybe I'll give you an overview of what I'm going to talk about. There's a little bit on the platforms. I won't talk about all of them because some of them I think you'll hear in some of the other talks afterwards. So just the ones that we were using here at EURECOM traditionally and much more recently. And I think you saw one of them yesterday too in the demo session. Then I'll talk about the FR2 development progress in OAI. And then maybe just how we use this in a couple of projects. There are a few projects, and I just picked two of them because these are really the first two big projects where we have to go and put together an end-to-end FR2 system. So I figured I'd give you an idea what those are. So just in general, the platforms for FR2 or millimeter wave. There are USRP-based solutions, which you saw in the demos. What we had been doing at EURECOM for the last few years, playing around with this stuff. There was also a USRP-based solution with external millimeter wave frequency conversion and analog beamforming. That's the state of FR2 in a lab setting. And what we realized is, you know, we've started doing FR1 ORAN compliant radio units. It's not so easy to find an FR2 ORAN compliant radio unit or completely integrated FR2 solutions. For some experimental deployments, it's nicer to have a completely integrated box that you can connect to the network rather than having pieces that you have to put together and complement with your own electronics or something like that. So it's very difficult in FR2 compared to FR1. I guess that's because the market is not really ready for commercial FR2 solutions today, which is good for research labs. The only one, to our knowledge, that can be bought off the shelf is this pre-product. I would call it a pre-product because it's not really a product from LightOn, the one that we showed yesterday in the demo session. So we've been working a lot in the last year on integrating that LightOn device with EURECOM. It's quite an ordeal. The USRP-based platforms, they look like this. So in this picture, it's a USRP X410. And I thank Paulo for this picture. I stole it from our Mobile World Congress poster. An X410, which has intermediate frequency connections to a millimeter wave front end. In this case, it was a prototype device that we had the chance to get from Interdigital. They had teams inside of Interdigital that were prototyping FR2 about 4 or 5 years ago. And we got some early versions of this device, and now we're using the latest version that the team developed. And this basically will provide two connections at intermediate frequencies for connecting up to 2 millimeter wave front ends. These are 9x7 analog beamforming arrays with a single polarization per antenna element. So with two of them, you can do a 2x2 system. We were only running it with one of them at a given time. And there's also another control interface to control the beam switching of the radio unit, and that was done with the USRP's GPIOs. So the GPIOs are there to switch between transmit and receive and to select the beams on the radio. And I think inside the solution that you saw yesterday from National Instruments and TMY Tech that was put together with AlbiSmart, I think it's not that different from this because we're using the same, essentially the same USRP drivers on the different platforms. The light-on FR2 ORU is different. Inside it has an AMD RF SoC. So it has very wideband transceivers inside the FPGA with some ARM CPUs on the side. And they have a millimeter wave antenna array in there connected to the RF SoC. And this actually implements the full ORAN frontal. So it's a completely integrated box. You can see the picture of it there on the tripod. It was a different one yesterday that Karim was using, but it's the same device. So this is a fully integrated solution. I thought I would share here very quickly some of the things. So this, it's a medium power solution. It puts out around 49 dBm isotropic equivalent power. It has 2 polarizations per beam, and you can sweep across 64 different beams. This is also 25 gigabit Ethernet fiber. So it has a 2.5 times the other radio units that we've been using in the OAI community in terms of throughput on the frontal. That's because it has a lot more bandwidth. So this one can work with 64 vertical horizontal beam positions, so approximately 15-degree steps in each direction. It can also manage 2 concurrent beams at the same time on the one radio unit with 2 polarizations per beam. So it's quite a bit more, there's quite a bit more RF in here for actually doing high transmission bandwidth. So basically it's 2 beams with 2 by 2 MIMO on each beam. In terms of the spectrum configurations, it can do 100 or 200 megahertz channels with 120 kilohertz subcarrier spacing and handle up to 2 200 megahertz component carriers. So this is 400 megahertz total bandwidth. So what that means in OAI numbers today, if we were to take the air interface that we have, we could in principle support on a downlink 5.6 gigabits per second in the TDD configuration that we're all using to support 2 UEs running in different beams. Okay? So those are quite high numbers for OAI. And we're not anywhere near that today, which is why I think it's interesting to go to the end of integrating this device because it's the only radio that'll do this for us. And on the uplink, we should be able to get something like 1.2 gigabits aggregate uplink throughput. In principle, with, again, 2 UEs on different beams. Now, why is that interesting? Because we will be able to test the full stack at gigabits per second with something we've never done. So there will be issues all the way up the stack to get to these rates that these radios are able to support. So I think it's actually interesting for us to go and do this because it will make the software better all the way up on the stack. In terms of user equipment, I think you saw some of these things in the demonstration. We're all using these Quectel RM530F, which have the latest, maybe not the latest, but almost the latest Qualcomm chipset in it. These work in full 5G standalone in FR2. For me, this is the only device that I've seen today that will actually do standalone in FR2 that we can buy off the shelf. It's not really mobile, but it is a very nice platform, and it has much higher capabilities than we're able to do today. So the throughput that you can get with this will be the 5.6 gigabits per second if we could harness that with our software. There are some FR2 smartphones, for instance, the recent Galaxy S23's 24 US edition, which also have the same chipset as the Quectel IoT device. But for some reason, these are only operating in NRDC, so they won't do standalone on the FR2 carrier. You need a FR1 carrier to run the control plane or additional throughput. So that's for what we've seen in the phones today. We can configure it to do NRDC, but that's also something we can't do in OAI today. So that would be interesting, for some of our research projects. I'd really rather work with a phone than this big IoT module, because it's really clumsy. But there we have to do work in the software to get it to that point. And the other issue is buying the phones, because we need friends in the US to buy them for us. We can't buy these here in Europe. So that's another issue. There is also work on the OAI UE, and at AlbiSmart they're doing this. we can use a similar solution to the USRB-based GNOB platform. This is actually very interesting in the research projects because it can give us configurable measurements of the UE receive chains, which we can't get from a commercial off-the-shelf UE. So that there is interest in taking the OAI UE into these places too for that. So if I switch now to the support for FR2, because this is another big issue. The current support in OAI, we can do up to 200 megahertz bandwidth. That's, I'll Be Smart has shown that that's possible. But that's on a fixed beam from the MAC scheduler perspective. We can't switch beams in the MAC today. It's also single layer. It works with the X410, or actually we made it work with the X320 here at EURECOM recently also, the N320, I'm sorry, and some external FR2 RF. But this branch is not sufficient to harness this radio unit that I described. It has much more capabilities that we can exploit, but that are not in OAI. So our good colleague Francesco has been working over the last couple months on a branch that is in merge request now, and I think it will go in very soon. This provides index beamforming support in the MAC layer. Okay, so what that means is basically he's exploiting the FAPI interfaces that were already there to be able to do the beam indexing in the physical layer. So that brings the beam sweeping on the random axis, so we can sweep all the SSB, SSIB1 beams and the PRATCH on the uplink with this and be able to position the UE in a particular beam. It's also, you have a configurable number of concurrent beams and a configurable beam switching period down to one slot. Right, so with this, we can start to go in the direction of actually doing the right beamforming procedures in FR2. Now, there's other work that's going on by Karim Boutiba, who gave the demonstration yesterday, where we needed extensions in the OAI's libxran patch for the frontal. Basically, we had to put in multiple section descriptions in the user plane so that we can do symbol-based beam indexing. For FR2, you have to be able to index basically every OFDM symbol in a slot. And there were also necessary timing adjustments for the 120 kilohertz subcarrier spacing compared to FR1, and to support the 125 microsecond slot times, which is, from a real-time perspective, much shorter in time. So there were some changes that had to go in for that. This is already working. That's what we were showing yesterday. We have the FR2 with 7.2. So the next steps after those two pieces go in, we have to start looking at the MAC scheduler beam switching granularity down to the symbol, not over one slot. And this is definitely needed for the SSBs and for the CSI-RS. And it's actually also necessary for the uplink signaling for PUCCH and SRS, which are at the end of slots in a particular symbol. They're not necessarily on the same beam as the uplink shared channel before it. So we have to switch within the slot on the uplink. And the scheduler needs to know how to do that properly. And also the CSI reporting for large SSB beam counts. You saw the light on radio unit has 64 beams, so we would in principle have 64 SSBs. We have to be able to handle the feedback also properly for all of those SSBs. We also need RF simulator extensions for FR2. This is something we've been talking about with Laurent and Francesco, so that we can actually simulate FR2 properly with multiple beams. With RF simulator, that we cannot do today. So with this, with these extensions, we'll be able to do that. And then I think we need to go to testing the 200 megahertz carrier with 2x2 to at least get to 2.5 gigabits per second. And that will start stressing the higher layers, and we'll find all kinds of things that are going to break in RLC, PDCP, and the UPF and all the way. That's almost certain that that's going to happen. But I think it's necessary, and then we can go towards more complicated things somewhere down the line with multiple component carriers and NRDC. So just 2 words on the projects, and then I'll stop.
Yeah.
Converge is an EU project where we're working with I'll Be Smart and other partners like INRIA next door, where we have to actually deploy this FR2 with camera equipment to enhance vision in cellular networks. So we want to use FR2 devices with reconfigurable surfaces and enhance the ambient intelligence of the network, combining all of these sources of spatial information, and also the digital twinning aspect, I don't know if anybody knows, but this morning at 8 o'clock there were people down in our floor from the 6G flagship in Oulu that were scanning our lab to build a 3D model, and I think they're going to Porto next week, and they're at INRIA this afternoon doing the same thing. So we will have a model of our FR2 deployment so that we could actually come up with a digital twin of that model. The other project that is being run by locally at EURECOM by Adlen is all about autonomous robots, and we're actually using Qualcomm University robotic equipment here combined with FR2. And technologies that come from other places like the CEA Leti in Grenoble, which provide these reconfigurable intelligent surfaces. So these are things that you stick on the wall, and you can control their reflective patterns so that you can reflect beams in the direction of places that are shadowed, right? To increase the coverage of in an indoor environment, for instance, or a factory environment, that sort of thing. So those are some of the use cases why we're actually going to the trouble of putting all of this FR2 stuff into the community. So just to conclude, FR2 is coming, and it will be with proper beamforming capabilities, thanks to Francesco. And we're testing new communications components like these reconfigurable surfaces. Only one thing, if anybody has any way to help us get other FR2 ORUs, we're ready to buy them off the shelf.
And I believe contributions to OAI are also welcome, no? A lot of challenges ahead. Thank you, Raymond. Thank you, Raymond. So I think we have time for one or two questions. Is there any question in the room?
Thank you, Raymond, for this very nice presentation and the work that you've done with Olby Smart and Karim. One question I have is about the subcarrier spacing. This is not something that you will want to check at the moment. You will stay with the 120 kilohertz. Right?
We're kind of at the, with the USRP platforms, we could go to the higher subcarrier spacings, of course. But with the ORUs, that particular one is limited to 120. So it's kind of what the hardware is able to do. If there's interest in doing something more, we could. I don't know the capabilities of UEs either today, commercial UEs. But something that is full OAI, we could go to the new carrier spacings, for sure.
Okay, no. It appears that this is the one that is always used, so this is why I'm asking this question.
I have seen traces where the main communication was 120, but the SSBs were 240. There were some RUs like that. I think some of the Samsung RUs were like that.
Okay, thanks a lot.
Thank you. I think we have time for another question, final one, because otherwise we are running out of time. There is some.
Yeah.
Sorry.
I have a question about the risks. Can you explain a little bit what kind of risks you are testing right now?
I think there are two technologies. I mean, the one that I think we're aiming to test with is from a company called Greener Wave. They have a bit of difficulty in reproducing it in quantities, but in this project in Converge, all of these sites that are going to start deploying this equipment are supposed to use these Greener Wave risks. I don't know the exact technology. I think it's a kind of pin diode device. But it's basically a square about this size, and you can tile them together. So each tile, I think, is 40 by 40 centimeters. And basically, it has an electronic steering capability. So basically, you can tell it to, it has to be calibrated, but you can tell it to reflect a beam in a particular direction. So the projects are looking at how to connect also the risks to the scheduler of the system, or if it's a slower speed to an X app or something like that of the system, or a D app of the system, to be able to control the risks to improve it. So it's that kind of a device. The other one is more of a reflective risk that doesn't have as much granularity to control. It's one from the French lab, CEA, but I don't know the exact details. We have that in the lab here, but it doesn't quite work yet.
And what are the frequencies you're using for that?
These are all operating around 27 gigahertz.
Okay, we may continue the discussion in the coffee break, so just to give opportunity for a final quick question.
I would like to ask the following. on what level of OAI are you using the FR2, the light, the equipment? Do you have access on the layer 2 of the radio capabilities, or you're just sending the bytes in and bytes out of the equipment?
You mean the ORU it's a 7.2 interface, so the physical layer is running, the DU is running, it's an OAI DU.
Yeah.
So we have access to everything.
Okay.
Absolutely everything. In fact, that's what we want to use in the project. For vision, I mean, you want to be able to get the SRS measurements on the uplink to be able to use them in the edge to infer things. So we have access to absolutely everything.
You have this capability only for, let's say, the G-Node B, not for the UE equipment.
If you run the UE with the setup that Albie Smart was demonstrating, you would have the equivalent at the UE. And you have full time domain granularity of the UE receiver.
I think the next presentation will give more details about the setup, also from NI. So, Raymond, thank you very much for your interesting talk.